So in this video, I actually want to walk through a demo and a case study of how spectral clustering works on a real-world data set. So let's go ahead and do our imports. And in this demo, what we're going to do is we're going to use spectral clustering to figure out the conferences of universities that participate in NCAA Division I, which is college sports, specifically in this case, college basketball. So Division One, it contains 350 schools, or 353, I think. UC Berkeley, also known as Cal, is one of them. By the way, if someone asks you where you go to school and you say, I go to Cal, and they say Cal what? Only say there's only one Cal. There's only one Cal, and that's UC Berkeley. The other schools, Caltech, Cal Poly, whatever, those are Caltech, Cal Poly. If you just say Cal, you're referring to UC Berkeley. I just wanted to mention that as an aside. But anyway, so there are 350 schools, 353 actually. And within this Division One, they're divided further into conferences. So there are 32 conferences in Division One, and each conference has about 10, 11, 12, maybe some more, maybe a little bit fewer, around 10 teams in each conference. And for a given college basketball team over the course of their season, they will primarily play teams within their conference. So take Cal, we play Stanford, USC, UCLA. We play all of those teams because those teams are in our conference, which is called the Pac-12 conference. There's also other schools that Cal plays. They play non-conference opponents, for example, San Diego State or Yale. And any given year, you might play just random other schools, and they're part of your schedule. Those games count just the same, but they're not in the conference. So what we can do is we can use this data and we can create a graph. And in our graph, each node or each vertex will represent a specific team, a specific school, and then we'll draw an edge between two schools if those two schools played each other. And if those two schools played each other multiple times, then we'll increase the edge weight. So we'll have the edge weight equal to the number of times the two schools played each other. Most pairs of schools will not have an edge. There's 353 teams, like each team is only playing about 30 games over the course of a season. So they're not going to play everyone. They're only going to play a small subset of all of the teams out there in D1. And then what we can do is once we have this graph, we can perform spectral clustering to try and find the real dense regions, the groups of schools that are really closely related to each other, that play each other a lot. And those dense regions will likely correspond to the actual conferences. Regions that are not as dense, probably those are just probably random teams. They don't correspond to a specific conference. We want to find the dense clusters that correspond to conferences. Because again, within each conference, you play teams a lot more than you would play teams that are not in your conference. Hopefully that was clear. So what we can do is we can load in the data. And here I just have a list of all the games that took place over the 2018-19 season. So the reason why I'm using this year is because this was the most recent year that was completely unaffected by the COVID, the restrictions around the pandemic. Because yeah, the next season it's ended early, and then the season after was just a bunch of weird scheduling. So this is kind of the most like representative season, I would say. So anyway, we can load in the data and we have a list of games. So we have the date, who won, who lost, how many points were scored. We don't really care about the points. We just care about who's playing each other. And we can see that there's 5,603 games in our data set. So again, 353 teams, 5,600 games. And here's another paragraph just describing kind of how we can represent this data as a graph. First, we have to do a little bit more data wrangling. But what we can do is we can look at California, our school, UC Berkeley, Cal. From now on, I'll probably just say Cal. We can see here all the schools that Cal played. So all these schools we played twice, Arizona, Arizona State, USC, UCLA, Stanford. And all of these schools are schools that are in the Pacific 12, the Pac-12 conference. However, Cal also played a bunch of other teams, some of which are also still in the Pac-12 conference, like Utah, Oregon, Oregon State, but a bunch of other schools that are in completely different conferences, like Cal Poly or Yale or San Diego State or Seattle, Temple. These schools are non-conference opponents. These schools are in different conferences than Cal. So what we can do is we can look at all possible matchups that were played. Because clearly, I mean, not every one of these games is a unique game. I mean, two teams play each other multiple times, so we want to kind of collapse this down. And we can do that using this, and we can see that there are 3,987 unique matchups in our data. And you can see that the most, like, no two teams played each other more than 3 times. So it looks like a few teams played each other 3 times. For example, Seton Hall played Villanova 3 times, which is pretty rare. Gonzaga played Texas Tech once, but there's no 4s here, like no two schools played each other 4 times. So yeah, we have 3,987 unique matchups, which means we'll have 3,987 edges in our data set. So now what we're going to do is we're going to load in the actual data about these conferences. So recall that clustering is unsupervised learning, which means that when we actually do clustering, the algorithm isn't going to see this data. It's not going to see which conference the teams are actually in. But we'll use this data to kind of verify whether or not spectral clustering found the appropriate clusters. We kind of have an idea of what the cluster should be, so we can verify like how effective or how accurate our clustering method is by seeing if it can pinpoint these clusters on its own. Let's go ahead and do that. I have a data frame called teams. The index will be the name of the team, and then the conference column will contain the conference that that school is in. So here you see Alabama. Alabama is a pretty famous program, mostly for football, but of course they have a basketball team too. And you see Alabama is in the SEC, the Southeastern Conference. And then there's other conferences and other schools that you may never have heard of. For example, Abilene Christian in the Southland Conference. But these schools are all D1 schools, just like Alabama, just like Cal, and so on. So now we can investigate the actual conferences, and we can print out all the information about conferences. And we can see that there are 32. Well, I guess I didn't actually show that, but we can see length of conferences. There are 32 conferences, and here they are. And you can see this count column indicates how many teams are in each conference. So we see, for example, the Ivy League, which is its own conference, has 8 teams. The Pac-12 has 12 teams, which you might expect it has 12 teams, given that it's called the Pac-12. But the Big Ten has 14 teams, and the Big 12 has 10 teams. So at least I'm proud to go to a school whose conference is actually accurately named and doesn't have a stupid name like Big Ten for a conference that has 14 teams. Anyway, so here they are. Here again, yeah, you've probably heard of Pac-12 or maybe the Big Ten, maybe not so much about Horizon or any of these other ones. But again, these are all Division I conferences. So now what we can do is we can create our graph, and we'll use this module called NetworkX. So NetworkX is basically the Python library for working with graph data. It's just like Pandas is kind of the Python library for working with data frames. NetworkX is what we use to work with graphs. And just a quick note about terminology. NetworkX will call vertices nodes. So in this notebook, you'll probably see nodes, but again, nodes and vertices are the same thing. So what this does is this just loads in, creates our graph. It adds all the nodes, 1 node for each team, and then it'll add the edges one by one for each matchup. And you can see we have 353 nodes, 353 teams, and 3,987 edges, 1 for each unique matchup. So of course we could try to plot this and look at this and see what's going on. But unfortunately, if we tried to plot this, it would just be insane overplotting, too much information going on. So what we're just going to do is we're just going to look at a small slice, a small subsection of this whole graph. And specifically what we're going to do is just look at schools that are in California. So I think California has something like 20 or 25 D1 schools. So we'll just look at the graph corresponding to those schools. And we'll ignore all of the other schools for now. So here's how we can plot it. Don't worry about the code, just worry about the result. And here's what this looks like. So you can see in this plot here, each node again represents a school. And I've colored the nodes or the vertices by the conference that the schools are in. So for example, you see USC, California, Stanford, and UCLA. They're all yellow because they're all in the Pac-12 conference. But there's other schools, for example, the gray schools, Pepperdine, Pacific, San Francisco, St. Mary's. These are all schools in what's called the West Coast Conference. So yeah, there's a few different conferences here, and that's why we've colored the nodes. And you can see, so let's look at UCLA. So UCLA, it played Stanford, it played California, it played USC, and it played, it looks like UC Davis, or maybe one of these other ones. It's really hard to tell. We're still definitely overplotting here. And we could just investigate this a little bit. One thing to note is that within the conferences, teams that are in the same conference play each other more. For example, these blue points all seem to be pretty well connected. The gray points seem to be pretty well connected. But this red point, notice how there aren't any other red points here because this is the only California school in whatever conference this is. And it's not really playing, like it doesn't really play too many other California schools because all of its conference mates are out over here somewhere. We haven't plotted them. So yeah, just to kind of visualize what this graph actually looks like. So now we can finally get into clustering. We'll run clustering now. So based on our domain knowledge, I know that there are 32 conferences out there. So it makes sense that we want to cluster our graph into 32 different clusters. If I didn't know how many conferences there were, then maybe I would try a bunch of different values and see which one had the best. But I already know, based on my expertise, based on my domain knowledge, that I want to cluster this into 32 clusters. So we have our graph. So now the first step is to calculate the Laplacian matrix L. So to do this, first we can create the adjacency matrix. So this is how we can do this with Network X. It has a nice method that'll do it for us. You can see there's a lot of zeros here, but there's one you can see in this little slice. I guess whatever the third school and the last school was, they played each other. We can calculate D by just taking the column-wise sums. Notice how here it's not really sorted. It was just circumstance that it got sorted in the lecture slides, but notice that D does not have any inherent sorting to us, but it is a diagonal matrix. So it looks like this. And then we can calculate L, which is D minus A, and here's L. So this just kind of walks through how we might literally calculate L, or we can just make it directly with Network X. Network X will just do it directly for us with this line of code. Again, remember that G is our graph that contains our data, our vertices, and our edges. And here's what L looks like again. As for why I have this 2 array here, well, if I got rid of it, then we would end up with this weird compressed sparse matrix format. Really, we just want a normal NumPy array. We're not going to care too much about memory. This isn't going to eat up a whole lot of memory. So that's why we use a .2 array. So now that we've calculated L, we need to determine the eigenvectors and eigenvalues of L. And here's how we can do this with NumPy. We can call this function on our matrix L. Unfortunately, the default in NumPy is to sort the eigenvalues and eigenvectors in ascending order. So to go along with the convention in this class, where they're in descending order, we're just going to reverse the result. So that way, the largest eigenvalues will show up first, and the eigenvectors corresponding to the largest eigenvalues will show up first, and then the smallest eigenvalues will be at the end. So we can calculate that, and we can look at our eigenvalues. And you can see, I mean, it's not super interesting. It looks like 44, 44, 44, okay, 38, whatever. We're going to care about what's down here. Notice how the last one is 0, and here are the smallest ones down here. And again, we don't really care too much about the eigenvalues themselves. We just use them to sort our eigenvectors. I guess one thing that is kind of interesting, which I didn't actually notice until I was making this demo, is that there is a little bit of a gap, a bigger gap here between the 32nd and 33rd largest eigenvalues, or smallest, I should say. There's a much larger gap between these two than there is between any other, at any other point in our data set. And maybe this is an indication that 32 actually is the right number of clusters that we should use. But I have no idea if this is actually theoretically valid. I just noticed it. Maybe it's interesting, maybe it's not. But yeah, it's just something that kind of jumped out to me. And here's our eigenvectors. Again, we don't really care. It's 353 rows here. We're not going to be able to glean too much just by displaying them. But here they are. What we're actually going to do instead is plot these values. So of course we want 32 clusters, so that means that we're going to take 32 eigenvectors. So we'll have 32 columns. So each vertex, each team, will have 32 dimensions. You can think like 32 features, if you will. But of course, we can't really plot all 32 at once. It's just impossible. So what we're going to do is we're just going to plot 2 at a time. And the first set that we'll plot the eigenvectors corresponding to the smallest eigenvalue, which is 0, and then the eigenvector corresponding to the second eigenvalue, which is this. So here we go. Here's the plot. I've colored the points by the conference that they're in. And you can see that it's not really super exciting. All of these points here lie on the same line. And that's because the first, or I should say the last eigenvector, the eigenvector corresponding to the smallest eigenvalue, is always going to be a vector of all ones, or scaled copy of all ones. So this plot on its own isn't super interesting because we're really only looking at one dimension here. Yeah, sure, it's a scatter plot, there's 2 dimensions, but every point has the same value for V353 or 352 because it's 0 indexed. So yeah. One thing to kind of note though right away is that we've already kind of isolated one conference. This Big Sky conference is on its own up here. It's not near the rest of the points. And it's kind of interesting. We're just looking at really one dimension, and we've already been able to kind of separate or set aside one conference, which is the Big Sky conference. So anyway, more interestingly, we can look at the next 2 smallest eigenvectors. So that would be, I guess, really the V352 and V351, because again, this is 0 indexed, so it's off by 1. And this plot is a lot more interesting. Looking at this, we can actually see more clusters, more information. So again, here's our Big Sky conference, still all the way out here on its own. But there are other kind of blobs as well. For example, here's the Southland Conference with our Abilene Christian that we mentioned earlier. And this is definitely a well-defined cluster right here. Similar case for down here with the Southern Conference. These orange points are clearly like kind of on their own, separate from the rest of the data. Another interesting thing is that there's a whole big group of points up here that is definitely like, they definitely consist of multiple conferences. Like they're not all the same color, but they're shunted away from the rest of the points. And this is kind of interesting, and I'll just tell you that these schools here, these are schools that are mostly in the northeast of the United States. So these are all smaller schools, kind of smaller programs. They're not like the big name college basketball programs, but again, they're D1, so they're in the data set. And you can see here, like Yale, it's in Connecticut, Niagara in New York, Binghamton, New York, Lehigh, Pennsylvania, Navy in Maryland. So like these are all kind of smaller time programs that play in the Northeast US. And it looks like, just based on this, that they all kind of play maybe similar schedules. So yeah, they play their conference, the teams in their conference more often than other schools, but maybe they all play kind of the similar group of non-conference opponents. Here you see, yeah, Harvard, Massachusetts, Sacred Hearts in New Jersey, and so on and so forth. And another thing, like one final thing before we leave this, is that over here, here's the Big Sky, kind of on its own. Schools in the Big Sky, it's actually in the northwest of the United States. So you see here like Eastern Washington, Montana, Idaho, Portland State. These are all schools that are way up kind of in the top left corner, the northwest corner of the US. Down here, again, we saw schools that are in the south, Southland Conference, Southern Conference. These schools are all in the south. And these schools up here are in the northeast. So I think it's kind of interesting that if you were to say maybe flip, like reflect this plot, so to speak, kind of flip it over, or maybe look at it from the other side, you'd see the schools in the northwest would be over here, kind of in the northwest. Schools in the northeast would kind of be over here, and schools in the south would be down here. And it kind of resembles a map of the United States to some very imprecise degree. This is completely like coincidence, but it does goes to show that this is kind of like this plot kind of displays how well connected, like how similar schools are in terms of the schedules that they play. And schools that are on the West Coast and the Northwest play very different schedules than teams that are in the Northeast. And teams that are in the South, they kind of get the best, like they play kind of in the middle, but they're down here, they're down south. And schools that are in the North are up here in the North. So that's just kind of interesting. Again, probably completely coincidence, but it's just a neat little observation. So now it's time to actually cluster. So we'll select our last 32 eigenvectors and just verify that this data has the proper shape. So we have 353 vertices and 32 columns and 32 eigenvectors, 32 clusters. And then let's cluster with k-means. So we'll set k-means 32 clusters, increase the maximum number of iterations so that way it doesn't run out, it doesn't we guarantee that it converges, and then a random state just so we get the same results over and over again. And then we'll fit to our eigenvectors data, and then we can see the labels. And these labels, well, these labels aren't going to tell us the actual conferences. Remember from the very first video on clustering, when we talked about like Netflix coming up with the weird categories, one of the things with clustering is that it just finds the groups, and then you can give names to those groups after the fact. So these labels, for now, they're just numbers, they're just labels. But what we can do is we can add this set of labels to our teams data. So again, here's our data frame with teams. I've included all the eigenvectors, but here's the conference. And now here's the cluster label. And ideally, if the k-means was actually able to find the clusters appropriately, there'd be a one-to-one mapping between the name of the conference and the actual cluster. So all the teams that are in the Southland Conference should have cluster label 15 if k-means worked as we expected. If we see a cluster label 15 for a team that's not actually in the Southland Conference, then k-means failed. So let's see, let's verify if there is actually a one-to-one mapping between the true conferences and the cluster labels. And we can do that with this cell. And it turns out, yes, yes, it did work. For example, the ACC, all the teams in the ACC were given cluster label 6. ACC did not split amongst multiple clusters. Cluster 6 exactly corresponds to ACC, and that's the case for all the other conferences and all the other labels. There's a one-to-one mapping here. So in this case, spectral clustering worked. We didn't tell the algorithm anything about which conference each school was in, each team was in. We just gave spectral clustering a graph and said, here's the teams that each team played. Here's the games that were played in the season. Go figure out these conferences. Go figure out which teams kind of belong together. And it was able to do that. It was able to successfully pinpoint the 32 conferences. So that's it for this demo. That's it for this lecture. And that's actually it for the main content of the class. So I hope you enjoyed this lecture. I hope it was interesting. New material, again, to Data 100. And yeah, hopefully I'll see you in the live conclusion lecture on Thursday. And good luck with the rest of the class and with the rest of your career at Berkeley and beyond. So yeah, that's it.